So, in the previous session we saw invariance properties of the Lebesgue measure. Now, our aim is to prove that the Lebesgue sigma algebra is the completion of the Borel sigma algebra with respect to the Lebesgue measure, which means that any Lebesgue set is actually a Borel set union a set which has measure 0, right. So, if you recall the completion properties, what we do is we take a sigma algebra, we have a measure on the sigma algebra, we just put all the subsets of the sets of measure 0, we get a bigger sigma algebra which does not change much, but that becomes a complete sigma, that is called the completion of the original sigma algebra. So, that is what we will do now. So, let me state the theorem. This is actually finer properties of the Lebesgue sets which we need to actually prove, which will lead us to this proof of the theorem of completion. So, let me write the statement of the theorem first. So, let us say theorem. So, we have Rn, we have Lebesgue sigma algebra of Rn and the Lebesgue measure is the completion of Rn. You look at the Borel sigma algebra of Rn. So, that is a smaller sigma algebra and the measure, right. So, M is the Lebesgue measure, right. So, Lebesgue measure restricted to any smaller sigma algebra is also a measure. So, there is no confusion here. B of Rn is a smaller sigma algebra than Lebesgue sigma algebra. Of course, this it assumes that they are not equal. So, we will construct some sets to prove that they are not the same, but there are other cardinality arguments which will tell me that tell you that these two sigma algebras are not same, because this is what is known as a countably generated sigma algebra. So, it has the first uncountable cardinality and this has much more. Okay. So, that is one way of seeing that the inclusion is strict, but let us not bother about it right now. We will just prove that this is the completion. Well, how do you prove that? This requires some results. So, let's start with a lemma. Some lemma. Okay. So, if E is a Lebesgue set, then it's very close to being a Borel set. So, that is the statement we want to make. Then there exists a G delta set. G delta set. Well, what is a G delta set? So, a G delta set is countable intersection of open sets. So, this is a countable intersection of open sets, right. Of course, so this would belong to the Borel sigma algebra, right, because open sets are in the Borel sigma algebra, and so countable intersection of open sets will be in the Borel sigma algebra. So, I want to say there is a G delta set, let us call it G, such that E is contained in G and the measure of G minus E is 0. Okay. So, let's say A and similarly B. So, this tells me that E and G, they differ only by a set of measure 0. That's the assertion. So, E differs from the Borel set G only by a set of measure 0. Okay. So, and any such statement will have a counter statement from inside, right. So, because E is contained in G, similarly we can find something inside E. So, recall the definition of measurability and so on. We had an open set which is bigger than the set. Similarly, you had a closed set which is smaller than that. So, the statement B follows from statement A simply by the same proof. Okay. So, if A belongs to L of Rn, then there exists an F sigma set what is an F sigma set? So this would be a countable union of closed sets, right? It's a complement of G delta set, right? And of course closed sets are Borel sets, so countable union of closed sets will also be Borel set. Okay. Well, so F sigma set F such that F is contained in E. So compare it with this one, F is smaller than E, and of course measure of E minus F is 0. Okay, so let's show some picture. So if this is E and let us say this is F, the F is a Borel set, okay, and whatever is remaining, the remaining portion that has measure 0, E minus F is 0. Okay. So what did we, so the lemma asserts that E can be written as F union E minus F, where E minus F has measure 0. Right. So measure of E minus F is 0. Which is precisely what we mean by completion, right. So any Lebesgue set is the union of a Borel set and a set which has measure 0. So that is why we get the completion. So I'll and by construction the Lebesgue sigma algebra is complete. So I'll comment on it after the proof of the lemma. Okay, so let's start with the proof of the lemma. Proof of the lemma. So well, we know that for every epsilon, so by definition, so we know that by definition for every epsilon positive there exists an open set O such that M of O minus E is less than epsilon, right. So and E was of course contained in O. So this we know. Okay, we do this for epsilon equal to 1 by k. So and k runs from 1, 2, 3 etc. right. For each 1 by k we can do this. So remember our idea is to get open sets and countable intersection, right. So we run epsilon over a countable collection of set of numbers going to 0. Okay, that is a standard technique. So we will get for each k, so for every k we get an open set OK such that E is contained in OK and the measure of OK minus E is less than epsilon, less than 1 by k, right. Epsilon is 1 by k. So what is the countable intersection you can take? You simply take the intersection of OKs. Okay, so let O be equal to intersection OK, right, k equal to 1 to infinity. So this is a G delta set, right, and O of course for each k E is contained in OK. Okay, so this of course tells me that E is contained in intersection OK, k equal to 1 to infinity. So the set O, so this is O, right. So O contains E, so we know that, and we want to look at measure of O minus E. Well, what is measure of O minus E? Well, O minus E is equal to intersection k equal to 1 to infinity OK minus E, which is of course contained in, you take any one set from here, right. Let us say OJ minus E for any j, right. So this would be less than or equal to measure of OJ minus E, right, by monotonicity, which I know is less than to 1 by j, and this is true for every j, right. I can choose any set from here, any set from here, and that will give me a 1 by j, and that of course goes to 0 as j goes to infinity, which means measure of O minus E is 0, which is precisely the statement of the lemma, right, the first statement. So, if I have a G delta set such that the difference has measure 0. Similarly, I have a F sigma set. Well, what will you do? You use the other definition of measurability, right, or the equivalent definition of measurability. So, we have, so E belonging to L of Rn tells me that for every epsilon there exists a closed set, F, but now F is contained in E such that the measure of E minus F is less than epsilon. This we have. So, we can write epsilon to be 1 by k as usual, k equal to 1, 2, etc., and we will get closed sets Fk contained in E such that measure of E minus Fk is less than 1 by k. And of course, because of, so this is the same proof. So, because of this, Fk union Fk is also contained in E, and this is a F sigma set, and M of E minus union Fk, this is less than or equal to measure of E minus any of them, right. When you throw out bigger junk, union Fk, and that will be contained in E minus Fj for every j, which is less than to 1 by j, which goes to 0. So, this is equal to 0. So, it is the same proof. Okay. So, these are statements sort of complement to each other. We have seen this before. So, this tells me that any Lebesgue set is actually a Borel set and a set of measure 0, and by construction Lebesgue sigma algebra is complete. Well, why is that? Well, what does that mean? That means if A is a Lebesgue set such that measure of A is 0 and B is contained in A, then B is also a Lebesgue set, right. This is what completeness means. Okay. So, let us check that. So, if I take A in Lebesgue set, Lebesgue measurable, and measure of A is 0. So, measure of A is 0 is same as saying the outer measure of A is also 0, but B is contained in A. So, by monotonicity we know that M star of B is less than or equal to M star of A, but M star of A is 0, right. So, that implies this is 0. So, if M star of B is 0, then B is measurable, that we have seen. Any set which has outer measure 0 is a measurable set. So, B is in L of Rn, which means that L of Rn is complete. So, you put together these two, this completes the proof of the theorem. Okay. So, this completes the proof of the theorem, right. So, we stated a theorem in the beginning that this is the completion of this one, right. What we have just proved from the lemma is that any Lebesgue set is the union of an F sigma set which is a Borel set and something which has measure 0, and this Lebesgue sigma algebra is complete by construction. Okay. So, that put together those two will give me the proof of the theorem. Okay. So, let's construct an example of a non-measurable set. So, just to conclude that, so remember one of the inclusions we had L of Rn sitting inside the power set, We want to say this is actually strict inclusion. That means we need to construct. So this is the power set. So we need to construct a subset of Rn which is not measurable, Okay, that is what we will do. Okay, so non-measurable set. Well, so this requires what is known as axiom of choice. I will comment upon it when the time comes. So what we do is first define. So look at closed interval 0 1. So we are going to construct a subset of 0 1 which is non-measurable. Okay, so we will, let me write down that we will construct a set n which is contained in 0 1 and n non-measurable. Okay, so how do we do that? First define an equivalence relation. Define an equivalence relation on 0 1 by, okay, x is equivalent to y if x minus y belongs to q. Q, remember, is rational. So these are rationals. So here the, not the cube, q here is rationals. Okay. So if x minus y is rational, then we say x is equivalent to y. So using the equivalence relation, we can partition 0 1, right. You put together all those numbers which are equivalent to each other by this definition, we will get one equivalence class and so on other equivalence classes. So by equivalence classes we can partition 0 1. So we can write 0 1 to be equal to union alpha A alpha, where A alpha are equivalence classes. We do not know anything about the indexing set alpha. Okay, so alphas can be countable, well, it will be uncountable, that is clear, but you know how big it is, how small it is, etc. we do not bother about it. 0 1 is partitioned, A alpha are disjoint. So this is something which happens with any equivalence relation, right. An equivalence relation partitions the set and any partition gives you an equivalence relation. Okay. So construct n from this. Well, what do we do? By choosing, so this is the tricky part actually, even though it will sound very obvious, this uses axiom of choice, choosing exactly one element from each A alpha. Okay. So this is what uses, so this uses axiom of choice. So this uses axiom of choice. So let me tell you what it is. So I am not going to get into what is axiom of choice. So what are we trying to do? So let us say we have an indexing set I, capital I. So axiom of choice ensures the existence of a choice function, let us say f from I, that is the indexing set, to union A alpha in I. Well, what is the property? F of alpha will be in A alpha. So you can pick one element from A alpha for every alpha. That is what axiom of choice tells you, that it is possible to do that, and that you put together to get the set n. So that n is of course contained in 0 1, right. These are numbers in 0 1. We do not know how it looks like inside 0 1. Okay. So claim is that n is not measurable. Claim n is not measurable. Okay. Well, Why is that? So that is n is not a element of L of Rm. So this is proved by contradiction proof. Suppose yes, okay, suppose n is actually a measurable set. So measure of n will make sense, right? It is a measurable set. Okay. Now what you need to notice is that, so let me write down this and then explain. Closed interval 0 1 is contained in union n plus, let us say, Rk. What are Rk? Rk are rationals inside minus 1 1 intersected with, so q is rational. So you look at all rationals in between minus 1 and 1 and look at n plus Rk. So remember, n plus Rk would be, you simply add Rk to every element in n is contained in minus 1 2. Okay, this is easy to see because n is contained in 0 1, right? N is contained in 0 1. So if I add anything from minus 1 to 1, I am going to end up inside minus 1 2. And of course 0 1 is contained in n plus Rk. So let's try to prove that, prove the first part. So let's see this. So n is chosen by exactly one element from each A alpha. So if I take one element from n, so let us say x belongs to n, then x belongs to some A alpha, right, for some alpha. So what would be x, what will be A alpha? So A alpha is the equivalence class corresponding to x, right. So this is simply x plus all rationals. So this is simply x where R is a rational, okay, and such that x plus R belongs to 0 1. That is all is needed, right. So all, if I know one element, all the other elements in the equivalence class is given by simply adding rationals, because that is how the equivalence relation is defined, right. X minus y belongs to q. So x and y differ only by a rational. So all elements which are equivalent to each other will differ by a rational. So that is how you get this rationals. So if I look at n plus R, where R belongs to rationals, I am going to get the union of this will give me every element in 0 1, right. Q intersected with minus 1 1 will do. So all elements in 0 1 will be inside this, because I am choosing n to be exactly one element from each equivalence class, and if I have one element in one equivalence class and I add rationals to it, I will get every other element in the equivalence class, right. So if I put together all of them, I will get 0. And of course, so this part is fine. So this is trivial because n is contained in 0 1, and if I add things from minus 1 to 1, I am going to land up here. Okay. So we have this. So if n is measurable, okay, so if n is measurable, then n plus Rk is also measurable, that we have seen. So translation does not tell me, translation will preserve measurability. N is measurable, so n plus Rk is also measurable. Well, it is not just that they are measurable, they are disjoint. So n plus Rk are disjoint. Well, what does that mean? If I take two rationals, suppose p and q are rationals and p not equal to q, then n plus p and n plus q are disjoint. Okay, let us see why is that. Okay, suppose they are not disjoint. So I take some element x inside n plus p and inside n plus q, right. Intersection is not empty. What does that mean? That means x can be written as some n1 plus p, and it can also be written as some n2 plus p, where n1 belongs to n and n2 belongs to n. That is the meaning. But what does, so this tells me n2 plus q, sorry. This means n1 minus n2, okay, equal to q minus p, which is a rational number. So n1 and n2 are two elements, but their difference is in q. So n1 will be equivalent to n2, correct? But that is a contradiction, because n1 is equivalent to n2, then n1 and n2 are in the same equivalence class, okay, but that is not possible, because n1 and n2 from each equivalence class we have only exactly one element in n. So if I take two elements in n, they can't be in the same equivalence class. So because of that, these are disjoint. So now let us go back to the situation at hand. So we have 0 1 contained in union n plus rk, where rk is a rational inside minus 1 1, and of course this is also contained in minus 1 2. So if this is measurable, these are, so now we have proved that this is a disjoint union. So if this is measurable, n plus rk are measurable, this is a disjoint union, we can take the Lebesgue measure. So Lebesgue measure of 0 1, by monotonicity this will be less than or equal to measure of union of n plus rk over that set, less than or equal to measure of minus 1 2. But the middle term, because it is a disjoint union, is the sum of n plus rk, where rk belongs to rationals, right, intersected with whatever, intersected with minus 1 1. But what would be this? This will be infinity or 0, right, because m plus rk is, m of n plus rk is same as m of n. This is the translation invariance of the Lebesgue measure. So if this is positive, then I will get infinity, or if it is 0, I am getting 0. But both will lead to contradiction, because I have 1 here less than or equal to, it is either 0 or infinity less than or equal to 3 here, right. So that is a contradiction, and that is why this set is not. So we started with the assumption that this is measurable, but it is not, okay. So that is how we construct a non-measurable set. So we'll stop here. So we have just seen an example of a non-measurable set which is contained in 0 1, which proves that the Lebesgue sigma algebra is smaller than the Borel sigma algebra. At some point of time we will also comment upon why there are Lebesgue sets which are not Borel. We will continue with Lebesgue measure for the next few lectures as well. The next topic would be to compare the Riemann integration and Lebesgue integration, and see that we are not losing anything, we are only looking at a much more general theory than Riemann integration.